delivering value through insightful interpretations of global literary works. Hi, this is Sally's Book Club. Today's featured book is Mathematics. You might think this is a math textbook just from the title. Actually, the book has a subtitle, A Very Short Introduction, which literally means a brief overview. This means it's a popular science book about mathematics. The author aims to showcase mainstream mathematics' charm and make readers appreciate its wonders. Written by British mathematician Timothy Gowers, professor at Cambridge University. He's also a Fields Medal laureate, mathematics equivalent of Nobel Prize. Gowers attempts to answer, what is mathematics? Did you ponder this when first holding a math textbook? Did your first math teacher ever explain this basic question? This seemingly simple question proves surprisingly difficult to articulate. Dower says he encountered two unavoidable challenges when addressing this. First, mathematical texts overflow with specialized notations and formulas. Memorizing symbols and understanding terminology presents significant hurdles. Like this elongated S with a circle. What does that mean? Only after advanced math courses would you recognize this as a contour integral symbol. Before defining mathematics, we're already drowning in specialized symbols. Second, mathematical reasoning requires strict logical progression, like geometric proofs requiring justification for each step. Remember those? But modern mathematical proofs make geometry look elementary. Complex proofs with tedious explanations become intimidating barriers. Ours admits these challenges, but focuses on conveying mathematical thinking over technicalities. Professor Li Dekan from Fudan University wrote the foreword for the Chinese edition, enthusiastically recommending this book. Academician Li praised Dower's efforts, saying he introduces mathematical concepts through concise and vivid language. While presenting complex ideas with effortless mastery, his strategic perspective better reveals mathematics' essence. Ultimately, the question, what is mathematics, isn't easy to answer. Let's explore Dower's answer through two aspects: mathematical elements and innovative approaches. Three fundamental elements of mathematics: models, abstraction, and proofs. Let's break them down one by one. First, mathematical models. Remember Ali Baba's story? The treasure cave requiring open sesame command? The cave holds endless treasures but requires specific commands to access. Open sesame to enter, close sesame to seal. Modern mathematical achievements resemble that treasure trove. Mathematical models are the open sesame, keys unlocking these treasures for practical application. With proper models, mathematics enables precise calculations and real-world implementation. Consider this artillery example. A soldier must maximize cannon range through elevation adjustments. Instead of trial and error, he builds mathematical models to solve the problem scientifically. Assuming no wind, flat terrain, and constant muzzle velocity, basic Newtonian physics applies. Using high school physics, maximum range formula shows 45-degree elevation is optimal. The officer rejects this as oversimplified. Enter the PhD advisor for advanced analysis. Accounting for air resistance through differential equations, the scholar derives precise elevation formulas. The officer was dumbfounded. Derivatives here, integrals there, completely incomprehensible. She ordered the PhD to proceed, but the scholar said, "Not yet, we still need data collection." 3 days later, he reported, "I've measured wind patterns along the trajectory. Now we can calibrate." After setting up instruments and an hour of adjustments, boom, only 10 meters farther than the soldier's shot. While the complex model improved results, the officer valued time efficiency over mere 10-meter gains. So he still let the soldier operate the cannon. This teaches us mathematical modeling requires practical simplification despite mathematics precision. Two simplification criteria: sufficient for purpose, easy to solve. Mathematical models distill reality's essence through simplification. Dice probabilities, population growth, molecular motion, all calculable through mathematical models. The second mathematical element, abstraction. Mathematician Courant's famous saying, God made natural numbers, all else is human work. Let's examine number system expansion. Human achievements through abstraction. Natural numbers are 1, 2, 3, and so on. If a teacher writes 5 and asks, "What's this?" students can only answer 5 without further elaboration. But drawing 5 cars without writing 5 gets 5 cars, demonstrating number abstraction from concrete objects. Adding another car beside 5, students instantly say 6 cars without counting. This quick response uses addition instead of recounting. Facing numerous drawn cars, counting individually becomes tedious. The teacher circles 5 cars together. With 7 such circles, students answer 35 cars through multiplication. 5 times 7 equals 35. Using multiplication and addition significantly enhanced counting efficiency, demonstrating numbers' abstract power. Positive integers abstract reality. Further number creation exemplifies human ingenuity. First human creation, 0. The additive identity. Despite initial resistance, why nothing? Its mathematical necessity became undeniable. Today, zeros are crucial role permeates mathematics, especially in binary computing, 0 or 1 representing circuit states. Disconnected circuits do nothing, hence perfect zero representation. Second creation, negative numbers through equation solving needs. If 5 plus question mark equals 7, 2, but 7 plus question mark equals 5 requires inventing -2 through additive inverses. This negative number creation enabled subtraction definition, a minus b equals a plus minus b. Human creativity snowballed. Fractions half, radical square root 2, imaginary unit I, creating complex numbers, e.g. 1 plus 2i. Mathematicians systematically extended addition or multiplication to new number sets. Gauss proved equation-based number creation limits after complex numbers, requiring limits or series for further expansion. Thus emerged transcendental numbers, pi, e, and conceptual infinity beyond conventional numbers. Concurrent operational creations, division, exponents, logarithms as inverse operations. Studying operational properties became crucial. Achievements impossible through concrete object counting. Gowers states in the preface, if this book conveys one message, it's that we must learn to think abstractly. Because through abstract thinking, many philosophical complexities can be effortlessly resolved, just revealing the paramount importance of abstraction capability.